Have you ever wondered how molecules, things that are literally completely invisible to the naked eye, somehow manage to snap together with the absolute precision of microscopic Lego bricks? Imagine you've got this long chain of atoms, and you need it to bite its own tail to form a perfect ring. Does it work every time? Oh, not even close. Sometimes they snap together instantly, and other times they stubbornly, completely refuse. Today, we're going to explore exactly why that happens in this explainer on Baldwin's rules. Let's dive into it.
Here is our quick roadmap for today. We'll start by introducing Baldwin's rules, then decode the terminology, look at the ring closure matrix, explore the rules for enolates, and finally look at some exceptions to the rules.
All right, Section 1. Introducing Baldwin's rules, the true foundation of ring formation. So let's jump right into the origins of these guidelines and, look at the fundamental problem they actually solved for chemists. Way back in 1976, a chemist named Jack Baldwin proposed a set of rules that really fundamentally changed how we understand molecule formation. Baldwin's rules are essentially the set of guidelines outlining the relative favorabilities of ring closure reactions in allocyclic compounds. And by allocyclic, we just mean carbon chains that aren't quite aromatic rings yet. In plain English, they help us predict whether a chain of carbon atoms is going to successfully fold up into a ring, or if the reaction is just going to completely fail. And the secret sauce behind all of this is orbital overlap. It's really all about whether the electron clouds of the reacting atoms can physically reach each other in three-dimensional space to form a bond. Now, before we get into the real nuts and bolts, there's a super important distinction we need to make. When Baldwin talks about reactions, he uses the terms favored and disfavored. Now, you might hear disfavored and think, oh, that means it's impossible. But actually, scratch that, that's not quite right. These terms are used in a strictly relative sense. Favored just means the reaction is incredibly fast. Disfavored means it's slow. So slow, in fact, that it can't compete effectively if a faster alternative reaction exists. But hey, if no other alternate reactions are favored, you might actually still observe that disfavored product eventually. It's basically a microscopic race, right? It's all about which pathway gets to the finish line first. Moving on to Section 2, decoding the terminology and breaking down all that jargon. Look, I know organic chemistry nomenclature can look incredibly intimidating, but we're going to break it down super simply right now. Baldwin classified these ring closures using three very specific, very logical pieces of information. First up is the ring size. This is simply the number of atoms in the newly formed ring, so a 5 means a 5-membered ring. Easy enough. Second is the position, which is labeled as either exo or endo. That just depends on whether the bond being broken during the ring closure is outside, that's exo, or inside, that's endo, the ring that's being formed. And finally, we have the geometry of the atom being attacked. This is classified as tet, trig, or dig, which just refers to the electrophilic carbon's hybridization. So it's tetrahedral for sp3, think your standard single bonds, trigonal for sp2, meaning double bonds, or digonal for sp, which indicates triple bonds. When you put all of that together, you get these incredibly specific descriptive classifications like 5-exo trig. To really anchor this abstract terminology to reality, let's just compare two different reactions side by side. Take a 5-exo trig reaction, for example. It forms a ring beautifully, with a literally 100% success rate. The orbital overlap happens perfectly, snapping the molecule right into place. But then, look at a 5-endo trig reaction. In that case, the geometry just does not work out. The physical attack vector is an impossibility. The atoms literally cannot bend into the right position for those orbitals to overlap, and the reaction yield is absolutely 0%. It fails completely. And that right there visually proves exactly why these geometric classifications matter so incredibly much. Section 3, the ring closure matrix. Let's visualize these rules. Okay, now that we're speaking the language of Baldwin, before I show you the ultimate cheat sheet for these reactions, you really need to understand why these rules even exist in the first place. These rules apply when a nucleophile attacks a bond at a very specific, ideal angle. You see, molecules aren't just flat drawings on a whiteboard. They're real, physical objects with strict physical constraints. They can literally snap under too much strain. For an exotet reaction, the ideal angle of attack is exactly 180 degrees. This is what we call the Walden inversion. For an exotrig reaction, it requires an angle of 109 degrees, which is the Bürgi-Dunitz angle. And for an endo-dig reaction, it's 120 degrees. If the chain of atoms is too short or maybe too rigid to physically bend and reach these specific angles without breaking, then that ring closure is completely disfavored.
And this brings us to Baldwin's ultimate cheat sheet. It lays out the favored and disfavored ring closures for 3 to 7-membered rings. Let's test our knowledge a bit here. Notice the distinct pattern in the endo categories for tet geometry. For 3, 4, 5, 6, and even 7-membered rings, every single endo-tet reaction is completely disfavored. Why? Because reaching that 180-degree angle from the inside of the ring is just geometrically impossible for rings of that size. Conversely, the exo pathways for tet and trig geometries are almost universally favored. So by just knowing your ring size, whether it's exo or endo, and the geometry, you can predict the outcome of countless chemical reactions without ever having to run a single experiment in the lab. Section 4. Rules for enolates, specifically aldol cyclizations. Building on what we've just learned, we're going to apply this structural framework to a slightly more complex class of reactions. You see, Baldwin's rules aren't just for basic alkanes. They actually adapt to other reactive species too, like enolates, which are incredibly common in aldol cyclizations. The terminology shifts just a little bit here to accommodate this unique structure, using specific terms like enolendo and enolexo to describe whether the enolate oxygen ends up inside or outside the newly forming ring geometry. This brilliantly illustrates the pattern for enolates. Notice how, whether it's an exo-tet or an exo-trig type, the eno-endo pathway is completely disfavored for the smaller 3, 4, and 5-membered rings. It's a no-go. But when the ring size gets up to 6 or 7, suddenly, those eno-endo closures become highly favored. So why does this happen? Well, it's because those larger rings simply have more slack. They have enough flexibility in their carbon chains to comfortably reach those required orbital overlap angles, whereas the smaller, tighter rings, they would just snap under the extreme geometric strain. And finally, Section 5, Exceptions to the Rules. The twist. So just when we think we have the absolute perfect rulebook and this neat little matrix to solve all our chemical problems, it's time to reveal the messy, empirical reality of science. The truth is, Baldwin's rules are incredibly powerful, but they are based on empirical evidence, meaning observation, and there are definitely known exceptions. Because these rules are so strictly based on the rigid geometry of standard carbon orbitals, things that break those geometric assumptions naturally break the rules. For example, cyclizations of cations often disobey Baldwin's rules completely. Furthermore, reactions that include a larger third-row atom, like sulfur in the ring, also break the rules. Sulfur is much bigger than carbon, and its bond lengths and orbital shapes are entirely different. This means it can achieve orbital overlap in ways that carbon simply cannot. Which brings us to a really fascinating thought to close on for today. Jack Baldwin gave us a phenomenal, game-changing tool for understanding molecular mechanics, but it definitely has its limits. If empirical rules like Baldwin's have so many exceptions based simply on things like atomic size or charge, it really makes you wonder, right? What other firmly established chemical laws currently sitting in our textbooks are really just placeholders? Are they just waiting around for the next big discovery to completely rewrite them? Thanks so much for joining me on this explainer, and remember, always keep questioning the rules.